Hello everyone, I am Parth Bhandari and today we'll be talking about superfluidity in helium and BEC-BCS crossover. The contents of the slides are Bose-Einstein condensate, then we'll talk about superfluidity and Landau's criteria for superfluidity, then we'll see how superfluidity works for helium-4. Moving on from this, we'll discuss microscopic theory of superfluidity and then move on to weakly interacting Bose gases. Then we'll talk a bit about BCS theory, which is very important to understand superfluidity in helium-3 and to understand BEC and BCS crossover. Starting from Bose-Einstein condensate, BEC is a state of matter which is formed when a gas of bosons at low density is cooled to temperature near absolute zero. In this state, most of the particles are in K equal to 0 state. If we take the case of non-interacting BEC and study the statistics, we can obtain the following relations. These following relations are plotted on the graphs as shown in the right. N0 represents the number of particles in the condensate, mu represents the chemical potential, and Cv represents the specific heat. Superfluidity. A superfluid flows with zero viscosity, which means it flows without any loss in kinetic energy. Both helium-3 and helium-4 become superfluid at 0 Kelvin. But there is a difference because helium-3 is a fermion while helium-4 is a boson. Another difference is that superfluidity for helium-4 can be observed around 2.17 Kelvin, whereas helium-3 is observed to superflow around 2 millikelvin. In 1908, helium was liquefied for the first time by Camille Ons, for which he received the Nobel Prize. On the right, we can see that a tube is inserted inside a superfluid and the tube is plugged with cotton. Now, due to the cotton, only superfluid can flow through this. This can be understood by understanding the two-fluid model, where we say that a fluid has two phases, a normal phase and a superfluid phase. If in some region we heat the fluid using the radiation, then the density of normal fluid will increase, due to which there will be osmosis and the superfluid will flow into the hotter region and hence out of the capillary, giving rise to fountain effect. To understand superfluidity and Landau's criteria, we define Landau's order parameter given by psi naught here. Then we write the current density in this form. Now putting the order parameter into the current density form, we get J naught is equal to h cross over m n naught delta theta, from where we can write the critical speed or the velocity of a superfluid in terms of theta. We can also define circulation in the following form, and as we can see, our circulation is quantized. Now Landau argued that a non-interacting BEC cannot superflow. For this we can see that the critical velocity to superflow is given by this form, and if we invoke that epsilon of p is equal to p square by 2m, then we'll see that V critical will be 0, while for an interacting BEC we'll find V critical is equal to under root nu by m, where u is the interacting potential. We can find the quasi-particle energy spectrum in liquid helium-4, which is defined by this following equation: epsilon p is equal to Cp, which is the photon one, and delta plus p minus p naught square over 2m, which represents the roton part. Now moving on to superfluidity in helium-4, here we can see on the right that we have variation in Cv of helium-4. The helium-2 is superfluid and helium-1 is a normal fluid. The heat capacity variation of helium-4 with temperature is given by this formula. The point at which the helium-2 gets converted to helium-1 is around 2.17 Kelvin as discussed earlier. This point is called lambda point, and alpha here is equal to minus 0.009. Now in the earlier sections we talked about superfluidity, where we considered BEC wave function, which is a macroscopic wave function. Now we will talk about microscopic theory using coherent states and field operators. Coherent state and field operators are defined respectively. Now writing an interaction Hamiltonian and using these two, we can write the Gross-Petavsky equation, which will be of use to us in the weakly interacting, to understand the weakly interacting Bose gases. This equation is obtained after minimizing the expectation value of the Hamiltonian over the coherent state. Now using the concept of ODLRO, we can attain our macroscopic state from the microscopic wave function. We can define the density matrix in the form of field operators. Now considering the momentum distribution using a smooth function f of k, we can rewrite our density matrix or density function in the form of n naught plus 2 over 2 pi cube plus times this integral. Now the f of k goes to 0 in the limit where mod of r minus r prime goes to infinity, and hence for the case of non-interaction we can again obtain psi naught as the same order parameter we defined earlier. Now to understand weakly interacting Bose gas, as we can see, we have just put a V effective in our Gauss-Pitavisky equation, and then adding a perturbation to our field operator, we can get the energy equation as E of k equal to h cross k square over 2m to the power 1 half times h cross k square over 2m plus 2 n naught g to the power 1 half, which will be linear for small k. Here, to consider weakly interacting Bose gases, we have taken the potential to be of the form of delta function. Now, coming on to BCS theory. BCS theory was given by Bardeen, Cooper and Schrieffer in 1957, for which they received a Nobel Prize in 1972. BCS theory describes the superconducting properties of weakly coupled superconductors. The electron is lying in the dB frequency energy limit near the Fermi surface. So according to Cooper, the presence of an interaction potential, no matter how weak it is, the electron near the Fermi surface can form pairs. We can write the ground state of our BCS wave function in this form. The Hamiltonian for BCS state is given by this. Now, taking the average of this Hamiltonian over the above defined wave function, we'll get our energy by this equation. Minimizing this energy, we can obtain our gap parameter as delta is equal to 2h cross omega d by e to the power minus 1 v naught d of EF, where d of EF represents the density of states near the Fermi surface. Now we'll talk about superfluidity in helium-3. Superfluidity in helium-3 is observed around 2.7 millikelvin and it is found to have two superfluid phases, BW and ABM. The pairing in helium-3 is different from what we have discussed in BCS section, as the Cooper pairs become bound in L equal to 1 state, that is P wave pairing, and for what we have in BCS section was S wave pairing. Here, since we do not have electron-phonon attractive interaction, we'll have van der Waals attraction to give rise to such pairing. Since we want to have this attraction, we can manipulate our potential with lambda. We can again write our BCS state or our state for this fermions in the form of this equation. Now, since we have interaction, we'll add this extra term f of k sigma comma k prime sigma prime to our total energy. So the total energy form will look like E is equal to E naught plus this part plus half of our interaction term. Now, since we have considered van der Waals potential, we write our potential in the following form: V of k comma k prime is equal to integral over e to the power minus k minus k prime dot r. Now, in such a case, only our dot product between k and k prime matters. Hence, we can write our potential in this form of Legendre polynomial, where VL is given as follows. Now, coming back to our Hamiltonian, we will write our Hamiltonian in the same manner in which we discussed in the BCS formalism. All we will do is to add this interaction term in it. Now, as we can see here, our gap function will have contribution not only from spin but also from k, and it is not constant for k. Now, invoking the Hamiltonian equation where h psi is equal to E psi, we can write this particular form where epsilon k is the energy of the Fermi surface, mu is the chemical potential. And here we can see that our gap parameters are not independent of spin and k. So we'll write a matrix of these parameters depending on another vector d, where d mu of k is equal to eta mu I f of I theta of k phi of k. Now for the ABM and BW states, this eta is defined as follows. Using all this information, we can write our energy in this particular form. Now, putting the eta for ABM and BW states back into D, we'll see that the cross product here comes out to be 0 and our final energy is given by this. This figure on the right is the BW state, whereas the figure on the left belongs to ABM state. As we can see, the BW state is in correspondence with BCS since the energy remains same for all K, but the ABM state is different as the energy goes to 0 for particular values of K. Now we will talk about BEC and BCS crossover. To understand this, we must understand that the interaction between particles is based on collision, and when we talk about collision, we have a parameter called scattering parameter. If we can tune the scattering parameter, we can understand the BEC and BCS crossover. I have skipped the mathematical part here, but now if we see figure 9, we see a continuous change in factors mu over EF and delta over EF as we tune our parameter. 1 over KFO times A when approaches 0 from the negative part is in the BCS limit, while when it approaches 0 from plus side it is in the BEC limit. And as we can see, this minus 1 to 1 regime is smooth, and hence we can say that our crossover is happening. Now, to see this experimentally, we need to understand what is Feshbach resonance. Feshbach resonance occurs for a specified pair of hyperfine indices when the zero energy of the two-body scattering state in the open channel crosses that of a bound state in the closed channel as shown in figure number 10. Now, we can plot the scattering parameter with a change in magnetic field that is given by the equation A of B is equal to ABG, where ABG is the background scattering parameter, and the plot is shown in figure 11. For the BEC we have A greater than 0, and for BCS we have A less than 0, and this green regime belongs to the unitary phase or the phase where crossover happens. Thank you, and these are the references that have been used.